Let's work through the concept of Lagrange multiplier in this video, and we'll do it based on the example that we have in this question. But first, let's work on the theory. Let's prove with the derivatives what Lagrange means, and in the next video we'll actually apply it on this question. So let's just write down the function of Lagrange here, and then we'll generalize it. So we would say that this is the function that we have, 24x minus x squared plus 16y minus 2y squared minus a certain lambda times x squared plus y squared minus 11. Now, why do we have this thing? We want to maximize this value. We want to maximize this value given that we have a certain limit. And this is a very practical and very realistic way to solve things, because everything we would like to produce, we have a limit. Let me give you an example. Suppose we want to produce milkshake, and let's say the milkshake, we use milk for it and chocolate. Milk and chocolate. That would be our x and y values. That would be the inputs in our function which produces our milkshakes. And in total we have, let's say, 11 kilograms of milk and chocolate together. Now the question is, how can we maximize the number of milkshakes that we produce given that we have 11 kilograms in total? That's basically a thing that we can literally solve with Lagrange. But now, why do we write the function in this way? So why do we have that we write down the function minus a certain lambda? The most important thing in Lagrange is to understand the intuition of lambda, and we write it because we want to show the relationship between our constraint, between our limit, and the actual result, the actual output that we are trying to maximize. So recall that whenever we try to maximize something, we want to be at the peak. Like when we had with derivatives, we wanted to have a derivative equal to 0, remember? Because in that case we are maximizing or minimizing the value. We have a flat derivative. And in our case, let's just stick to the maximizing example so that we can relate to the question better. So if we want to maximize, we want to have the partial derivative of our function with respect to x equals to 0. So basically we want to reach to such a point where the relationship between, let's say, milk and milkshake is maximized. So the relationship between milk and our milkshake is maximized. We're reaching to a certain level where we just cannot use any more milk more optimally. That's our peak point. We do the same with respect to chocolate. We also want to have a relationship where chocolate maximizes the value of the milkshake that we are producing. So again, something like that on this peak, because after a certain point, more chocolate is not gonna produce more milkshakes, because it's either not gonna be allowed by our constraint, or maybe the demand for milkshakes is not that high as to satisfy it. So in terms of practicality, there's only so much that we can produce. So that's what this Lagrange is trying to show us. And the last concept that I want to prove here is that the derivative of the Lagrange with respect to lambda also has to be 0. The derivative of the Lagrange with respect to lambda also has to be 0. Now, is that realistic? Well, let's see. If we take the derivative of Lagrange with respect to lambda, we have lambda over here, which means everything else is kept as a constant. So we take the coefficient -1 as a constant times all this thing. So -1 times x squared plus y squared minus 11 has to be equal to 0. So that has to be equal to 0. Well, -1 cannot be 0, which means x squared plus y squared minus 11 has to be 0. X squared plus y squared minus 11 has to be 0, which means, let me write it, you'll get the point in a second, x squared plus y squared equals to 11. Now what did we show right now? We showed that we satisfy the constraint. This was our constraint, and when we maximize the values, when we reach those peak points, we are actually exhausting, we are using all our milk and all our chocolate, and that's what we're trying to show here. So these are the criteria to maximize the value of a Lagrange. Now, if these are the criteria, let me think a second how to say it better. If these are the criteria, how can we prove that lambda is a certain rate of change? Lambda shows the relationship between the constraint and the Lagrange. So let's write it like that. Let's say that the maximum value, because we're trying to maximize, let me go to the right. Yes. So let's say that the maximum value that we're trying to produce is gonna be m. This is the maximum number of milkshakes we're trying to produce, and that depends on our constraint. That depends on how many kilograms of inputs we have. And this maximum constraint that we have is literally a function. This maximum output, this maximum result, in our case maximum number of milkshakes we're trying to produce, is a function that depends on the optimal points of milk and chocolate. Now, this is not it. I want to say something else. Think about this way. What if we increase the constraint? What if instead of having 11 kilograms, we will have 12 kilograms? Well, if we have 12 kilograms of milk and chocolate together, of course we can produce more milkshakes. It makes sense, we have more inputs, meaning that the optimal amounts that are gonna maximize our outputs are gonna depend on our constraint, are gonna depend on our boundary. So our x in the optimal point is also a function of our constraint. That's what we're trying to show here, that is, it depends on the constraint. And y in the optimal point also depends on our constraint. So let's write it over here that f of x and y is also a function on of our constraint. They both depend on the constraint. Meaning that if we find out the optimal results, if we find out the optimal results, we are getting to the maximum number of milkshakes. So x, y, and lambda is gonna give us the result for our maximum value, is gonna maximize our Lagrange. But one more thing, why is actually this maximizing our Lagrange? Is there any like mathematical proof that this is the case? Yes, there is, and let me show it. Because intuition is always good, but math is even better. Suppose we are let me write it over here. Let's write the general formula for Lagrange. So we just saw that the Lagrange is usually a function of x and y minus lambda times a constraint, which is the function, let's call it g of x and y, minus a constant, minus a number. And just to, to be comfortable with it, the function is the function. We see it here. I guess we can agree with it. We can be comfortable with it. But what is g of x and y? Is this one over here, x squared plus y squared, and then we just take the constraint, the constant, to the left. So that's gonna be our c. The 11 is our c in this case. Okay. Now, what we said is that if we have the optimal values, we will have this maximum result. Would that be true or not? Well, if we have the optimal values, then we would have a function that depends on the optimal values. We would have f that depends on x at the optimal and y at the optimal, minus lambda times g of x at the optimal, y at the optimal, minus the constant. Now, what did we say at the optimal level? What's happening at the optimal level? Let me go over here. We show that at the optimal level, this holds. The constraint is exhausted. It is satisfied. Meaning that g of x and y, at the optimal level, g of x and y is equal to the constant. We're literally using up all the kilograms that we are having. We're maximizing everything we have. So if that is the case, then g of x and y minus c is gonna be 0 because they would be equal. And if this thing over here is 0, lambda times it is gonna be 0 as well, which means that the Lagrange at the optimal point would be f of x and y. So that's going to be a function depending on x and y, which we just said. the function depending on x and y is gonna give us this optimal point. It's gonna give us our m value. Let's call it our maximum output. Now what we're trying to show is what is the relationship between lambda and Lagrange, or lambda and the optimal point. Well, to see a relationship between one variable and another, we need to see the derivative, because the derivative shows the rate of change between two variables. When x goes up, what does y do? In our case, when lambda when the constraint changes, how does the output change? So if you want to see the effect of the constraint on the output, we are going to take the derivative based on the constraint, with respect to the constraint. So if we take the derivative of, let's say, the maximum output with respect to our constraint, what happens? Well, we can see that the maximum output is gonna be equal to this Lagrange, because that's what the Lagrange gives us, a maximum value. But at the same time, recall that x and y at the optimal levels and lambda at the optimal level depends on the constraint. They are functions of our constraint, which means that we will have partial derivatives and the chain rule. So we will have the derivative of the Lagrange with respect to x times the derivative of x with respect to the constant, plus the derivative of the Lagrange with respect to y times the derivative of y with respect to the constant, plus the derivative of the Lagrange with respect to lambda times lambda derivative with respect to the constant, plus the derivative of Lagrange with respect to the constraint times the constraint derivative. Now, what are we trying to show here? In the optimal point, recall the following, that the derivative with respect to x, with respect to y, and with respect to lambda are 0 over here, meaning that the first three terms in our equation over here are gonna become 0. This is gonna be just 0, this is gonna be just 0, and this is also gonna be just 0, which means that the rate of change of the optimal output with respect to the constraint is the rate of change of our Lagrange with respect to the constraint. And when we look at the Lagrange and the derivative with respect to the constraint, what do we have? Well, look, if we differentiate this thing with respect to the constraint, we have minus lambda, which is the constant, times, from here we're differentiating this thing with respect to the constraint, and that's becoming minus 1 because it's having this negative coefficient. Minus to the minus makes a plus, so we would have lambda. And what are we showing now? That lambda is the rate of change in our optimal result when our constraint increases by 1 unit. Again, the Lagrange derivative with respect to our constraint is showing how the function changes at the optimal point. So once we maximize the value, how our maximum value changes when constraint increases by 1 unit. I hope this makes sense, at least more or less. It doesn't necessarily have to make us 100% from the first time, because it's not an easy topic to understand and to explain it either. There's not much theory and intuition available about it either. But I hope this makes sense, and in the next video we're gonna solve the question and see how that works out.